a function, you will be really close to 8, but you're not going to be 8. You're going to be like 7.9999 or something, right? But the limit doesn't care. The limit wants to know what you are headed towards. Okay? So I'm going to write that down. I'm going to write lim x approaches 2 from the left, so a little negative sign, of what? What are we actually looking at? This function, right? So I'm going to put f of x, and then I'm going to put equals 8. Questions? How about you try the other one? I want you to write down the limit yourself. Write down what the coming in from the right would be, and then I'll write it up here after about maybe 30 seconds, and let's see if we have the same thing. Let's see if you write it all down correctly. Everybody get that? Okay. This is what we'll call the left-handed limit, and this is what we're going to call later the right-handed limit. And all the definitions, I'll put them up here for you, don't worry. But left-handed limit, right-handed limit. Are they the same? Is the left-handed limit equal to the right-handed limit here? No, right? Back in the previous problem, were the left and right-hand limits the same? No. No. Let's go to the next example. Ooh. Okay. This is a rational function. You should recognize it as being a rational function. This dotted line that I've drawn here is referred to as the asymptote. Which one? Vertical asymptote. This is a vertical asymptote, right? So we have a vertical asymptote here, right? Okay. But I'm not actually interested in that right now. We'll talk about that, don't worry. I would like to know what f of 2 is. College algebra. Shut the shutters. What's f of 2? Shut the shutters. You're only allowed to look right here. What's f of 2? Look at the function itself. Try and plug 2 in, and what do you get? You get 0 over 0, don't you? Plug 2 into the function. 2 minus x over x squared minus 4. Plug 2 into that, you should get 0 on the top and 0 on the bottom, right? So you're going to get 0 over 0, and this is undefined. Do you all agree? It's undefined. So in college algebra class, you would say f of 2 is undefined. However, this is a calculus class, so we can also talk about this left and right-hand limit. Does it appear to you that as we approach 2 from the left, that we're actually headed somewhere? Does it? As we come in from the left, does it look like our function is headed towards a y value? Let's see it. So as we come in from the left, well, it's doing some crazy stuff over there. Don't worry about that. But here it comes. It's starting to get closer, getting closer to 2, getting closer to 2. What's my y value here? Can you read that or no? Negative 0.26. I get a little closer. Negative 0.25. Let me get even closer. 1.99. I'm going to go 1.99. And I'm at negative 0.2506. Doesn't it look like it's headed towards something? What would you venture a guess to be here that it's headed towards? Negative 0.25? Negative 0.25, that's a good guess, right? That's a good guess, negative 0.25. And what about if I come in from the right side? Is it approaching something? Yeah. It's going to be about negative 0.25. I'm not going to keep going, but you understand? So look, at 2, college algebra class, just looking at 2, hey, it's undefined. However, from the left side, in a calculus class, right, from the left side, we actually it looks like it's headed towards negative 0.25. From the right side, it looks like it's also headed towards negative 0.25. This is going back to that problem that we just had a second ago where I said, can we move that point over on top of the other point? When we do that, don't we get 0 over 0? But it looked like we were getting an answer. This is that sort of idea, is that look, at the point 2, we're getting 0 over 0. But as we are close to it, we actually have an answer. This is exactly how we're going to attack this sort of problem. Understand? Okay, so we're just kind of eyeballing that this looks like this. Looks like, well, why don't you write the left and right hand limits down on your own? And let's just use the number that we think it is. Make sure that you're writing it down with the correct notation. I'll put the answers up here. It's kind of fun, right? No? Okay. Okay, that's the notation you should have. Those are question marks. The reason why I put question marks is because we are truly trusting the computer here right now to tell us what this answer is, right? I mean, we have been trusting it, but we can't plug 2 in to verify this. It's impossible for us to plug in 2. We could go, I mean, if we wanted to, we could make a t-table, right, and just plug in like 1.99, 1.999, and we could just try and see, right? That's what I'm having the computer do for us. Maybe there's a way that we can actually get that answer from the function without having to even look at the picture. Okay, I'm going to write the function down here, and I want you to check something out. The function was f of x equals 2 minus x over x squared minus 4. That was the function, right? And we already know that if we plug in 2, it's undefined. But isn't this the same as 2 minus x over x plus 2 times x minus 2? Because that's a difference of squares in the denominator, isn't it? And then these two are not exactly the same, right? They differ by a sign, don't they? Like this is positive 2, this is negative 2, this is negative x, positive x. Yes? So could I do this? Could I factor negative out of the top, which would make that a negative 2 and a positive x, right? And then on the bottom, x plus 2, and then x minus 2. Aren't these now the same? The order of those can be switched, yes? Okay, so am I allowed to now cancel these? Yes? Y'all agree with that? I can cancel that? Okay, which leaves me with what? Negative 1 over x plus 2. So we're saying that this function, after some algebra, right? After some algebra, this function is actually equivalent to this function. What happens when you plug 2 into this? You get negative 1/4, which is negative 0.25, right? Which matches the answer we just got, doesn't it? So this is actually where we're headed. We're going to have to manipulate functions to the point that we can get this to happen. Now, we're not done. We have a big problem here, all right? Nobody stopped me, which means we have a problem. All right, I want you to just put this back burner for just a second, please. I'm going to give you two functions right now. F of x equals 1 versus g of x equals x over x. I've just given you two functions. Are they identical functions? If I asked you to graph those, would you get the same graph? Yes? Okay, so let me graph this one. This one would be the constant 1 function, right? Which would be a horizontal line raised up 1. So here's 1, and I would have a horizontal line through here like this, right? That's this function. Agreed? Okay, what about g? Well, if I plug in 1, what do I get? 1 over 1 is 1. If I plug in 2, what do I get? 2 over 2 is 1. 3 over 3 is 1. Any number, right? Except 0, right? You can't plug 0 into this. If you plug in 0, you get 0 over 0, which means it should be undefined. So these graphs are not the same. This graph, here's the value 1. It would be a horizontal line like this, but I would have a hole at 0. Okay? Now, if you were to graph these on your graphing calculators, you would not see this hole because your graphing calculator doesn't show you holes. So you would think it's a straight line, but it actually has a hole. Y'all okay? Now, if I asked you to algebraically simplify this, what would you tell me to do? Like, simplify that expression. What would you do? You would cancel the x's, right? And you would say that x over x should be 1, right? So then why aren't they the same? Because when you cancel two factors in a fraction, okay? If I had a little loudspeaker, I would do this in a loudspeaker. If you cancel two fractions or two factors in a fraction, there is an asterisk next to that cancellation. You are promising me that the factor you cancel is never 0. Now, this is not stressed too much in college algebra, but it is there. It's important. When we were right here at this step and we canceled these two factors, there's a little asterisk, and we are saying here, as long as x is not 2. As long as x is not 2, I am allowed to do this, right? I'm allowed to do this. What I'm trying to get you to see is that this function here is not identical to this function. Because if you graph this, it would not have a hole. It would not have a hole as opposed to this one, which it did have a hole. You okay with that? So, is that a problem? Because I told you, we'll plug 2 into this, and you said, oh, we get negative 1/4, right? And I just told you you're not allowed to plug in 2, right? But that's the limit. The limit says what? Limit x what? Approaches 2 from either the left or from the right, right? So what I'm trying to say is, look, this algebraic cancellation and this expression is valid if we're going to be talking about a limit, because the limit is not ever going to allow us to be 2. So this is legal in a calculus perspective. Now, if you take this expression and you start plugging in numbers like 1.9, 1.999, 1.9999, you are going to get a number that's very close to negative 0.25. So we're still able to recover that value without actually having to look at the graph. So this is all going to be good. I just want everyone to understand this is something that I remember as a student I wasn't clear on. I'm not quite sure when it ever became clear, but it became clear at some point that when you cancel factors, you are kind of signing a little waiver on the side that's saying, hey, look, I'm promising you that factor is never going to be 0. All right? Every time you've ever canceled, you've actually had that little asterisk. How are we doing on time? All right, let's see what the next example has in store for us. Oh, good old sine x over x. This one we're just going to have to do visually. I'm interested in what's happening at 0 on this one. So let's go to college algebra. What's f of 0? So that's sine of 0 over 0. What's sine of 0? 0. Sine of 0 is 0. So this is giving us 0 over 0, which is undefined, right? Which means that we should have a hole, right? We should have a hole there, which we do in this graph. I've made it clear that there's a hole. All right, let's look at it from a calculus perspective. Does there appear to be a left-hand limit? Does it appear that the function is approaching a particular value? Yes. What does it appear it's approaching from the left? It appears it's approaching 1. You may not be able to see that in the back. There's 0.5, 1.5, that's 1.0. So it appears it's approaching 1. From the right, it appears it's approaching 1 also. So we will be able to write that just from the visual inspection again. Approaching 0 from the left of the function, that equals 1. And then the limit as x approaches 0 from the right of the function equals 1 also. In this example, is the left-hand limit and right-hand limit the same? Yes. Yes. In the previous example, it was also. It was the negative 0.25. But in the ones prior to that, they weren't the same. Okay. It doesn't always, it can be different variations. It just depends on the problem. All right. On the last problem, I was actually able to get us to negative 0.25 by doing some algebra, right? I did the difference of squares and canceled and stuff, and I was able to magically get that. On this, is there anything that I could have done magically with algebra to somehow get the 1 out of here? So what I'm getting at is, if I didn't have this picture, if I didn't have the graph, and somebody had just said, hey, look, what happens as x approaches 0? If someone asked me that with no picture, how would you actually come up with 1 without it? You could start plugging in values, right? You could plug in like 0.9, 0.99, 0.999, 0.9999, 0.9, and you keep doing that, right? And then you could plug in something like 1.0, or not 1.0, sorry. 1.0 is 1. You could plug in, no. Let me get my number line, 0. We could plug in you help me get some points. How about some things to the left here? I think I just said the wrong thing. I think I was approaching 1. I take that back. Withdraw. I'm approaching 0 from the left. What are some numbers I could plug in to the left of 0? Negative 0.1. Closer. Negative 0.01. Closer. Negative 0.001, right? I could start plugging those values in here, get my calculator out, and see what my calculator's giving me, right? Spitting out. What are some numbers that would be to the right of 0? Same thing's just positive, right? So like 0.1, 0.01, 0.001, 0.0001, and I could get some idea, right? The graph was very useful though, right? Because the graph just showed it, didn't it? Yes? Okay. This is, well, I'll show you in the notes. That's a special limit. That's a special function. You're going to have to memorize that is 1. All right? You're just going to have to know it. And then later on, I'll give you the opportunity, if you want, I can prove it to you. Okay. Oh. Okay. What is going on here? See the function? Sine of 1 over x. What's f of 0? College algebra. Asking you to plug in 0 into that function, or pre-cal for that matter. Asking you to plug in 0. Undefined. Because you're trying to do 1 divided by 0, aren't you? That's undefined. Ooh. Look at this graph. This is something very strange is happening here, right? We have entered the twilight zone, I guess. Yeah, this is, let's come in from the left. Okay, here it comes. And everything's good, everything's fine right now, right? And then as we get in here, it starts, oops. Went too fast here. Let me come in like this. I want you to see my point? Here it comes. So look at this. Watch what's happening. See it? It's actually speeding up how fast it's oscillating. So this thing is actually doing, it's like trying to be a sine curve between 1 and -1. But see, again, if you have, let's say you have a big number over a small number. You told me that would be a big number? Big over small would be big? What if I have 1 divided by a number that's getting smaller? So take the number 1 and start dividing it by a number that gets smaller. What happens to that number? It gets bigger. So if you take 1 and divide it by 1/10, what would you get? 10. If you do 1 divided by 100, or 1/100th, you would get 100. 1 divided by 1/1000th, you would get 1,000. So as this number on the bottom gets smaller, this thing gets bigger, doesn't it? So what's happening here is that as my x gets smaller, right? As my x value gets smaller, gets closer to 0, this ratio gets big. So the sine function is trying to do its little thing, but it has to try and do all those oscillations over like a really long period in this tiny little spot. And so it starts going freaking crazy. It starts oscillating really fast. And the same thing happens from this side. It starts oscillating. Now, when you get to 0, the function's undefined. Does it appear that from the left, we're headed towards anything in particular? Can you say it's going towards 1 or -1 or something in between? Can you nail down one value that it looks like it's headed towards? No. Can you nail down a value from this side? No. Because of the oscillations, it's never behaving well and just kind of like coming in for a gentle landing, right, into a point. It keeps doing this crazy thing, yes? And so what we will say for this is that the limit as x approaches 0 from the left of this function, we do not put undefined. Okay, undefined is for college algebra questions. What's happening at a point? What we put instead is does not exist. Okay? The limit from the left does not exist. Now we will abbreviate that from now on. DNE, does not exist. That's not an O, that's a D. D, you can put the periods there if you want. Does not exist. How about the limit from the right-hand side? What's the limit as x approaches 0 from the right of this function? DNE, does not exist. This is the first time we've seen that a limit cannot exist. We got about 15 minutes. Y'all doing all right? All right. Let's look at the function f of x equals 1 over x. And most computers, if you ask them to graph a function like 1 over x, or a rational function, most computers will draw a vertical line where the vertical asymptote should be. And that's because computers are, in some ways, unable to cope with the division by 0. So if the computer tries to plug 0 in, it gets, it's undefined. So it says, hey, look, to the left of 0, I was way down here. and to the right of 0 is way up here, and so the computer is just like, crap, just draw a line between them. It just connects them with the line. That's an actual kind of like mistake within the computer. So please realize that this is supposed to represent a vertical asymptote. Now I can remove that line easily when I put these things together, but I wanted to illustrate it because on your graphing calculators, it will most of the time draw that line. So don't think, I've seen students like, as their answer for a problem, they'll be like, here's my graph. It's like, no, you can't have a vertical line in a function. It's not, it fails the vertical line test, obviously. Okay, so I'm interested in what's happening at 0. On all the problems we've done, the point that I have asked us to pay attention to is only one point on an entire graph, right? Like I could have asked us to look somewhere else on the graph, but I'm picking where there's something interesting happening. Like if I were to say, hey, what's happening at 1? Right here, you would say it's defined at 1, right? It is defined at 1. It would actually be 1, wouldn't it? 1 over 1. And then from the left and from the right, it looks like the limits exist, don't they? And everything's good. Everyone's happy. But I'm asking us to look at 0 because there's something more interesting happening here. So what is f of 0? College algebra question. I think I heard it. What? Undefined. Can I put does not exist here? No, you should not use does not exist for evaluating a function at a specific point. Undefined, that's good. How about coming in from the left? So let's take a look at what happens as we come in to this function from the left side. Everything's great. I mean, he's just coming on in, and all of a sudden, this thing just starts dropping off, right? It starts taking off. Now I have the y values are here. I don't know how far I'm going to be able to get in here, but it's going to start taking off pretty far here. I'm at negative 27, 28, 29, 30, look, 40. I'm really heading out there. I can keep going. Wow, it's really growing. It's actually becoming very big, but negative, right? And we all learned in college algebra that this is actually going to get just like infinitely big, isn't it? And so it looks like it's headed towards this very large negative number, like negative infinity. Now, infinity is not a number, but the limit is only interested in what the function is doing, like where is it headed, right? I hope we've already concluded that the limit is only interested in the behavior of the function, not what's happening at a specific point. So I think it makes perfect sense for us to say that the limit as x approaches 0 from the left of this function, it should be negative infinity. The function is approaching negative infinity. So we actually have an answer for a question. Our answer is negative infinity, which is probably the first time we've ever had to use that as an answer. Right? We've used infinity like an interval notation before, like for domains and stuff, but we've never really used it as an answer to a question. Here, the answer is negative infinity. Now, how about as we approach x from the right, approach 0 from the right? Of this function, it's going the other way. It's positive infinity. Are they headed towards the same places? So remember we had functions like the sine x over x, they were both headed to 1. Here, they're not headed to the same place, right? They're both headed to an infinity, but one of them's positive, one of them's negative, right? Okay, little side note here real quick. In the book, at this point in the book, this section, they like to say that this limit does not exist. And they introduce the negative infinity and infinity later, and I don't. I'm ready. Let's just talk infinity now, okay? So if you get an answer in the back of the, like if you look in the back of the book for an answer on a question like this and it says does not exist, and you put it that negative infinity and infinity, that's okay. All right? That's all right? I don't see the use in saying it doesn't exist and then later on saying it does, like it is something. So I just kind of don't do that. Okay, what about this one? Good old volcano function here. F of x equals 1 over x squared. Another rational function. Has a problem at 0, right? You can't plug 0 into this. Undefined. What's the left-hand limit? Infinity. Right-hand limit? Infinity. Positive on both, right? So now the left and right-hand limits are actually headed towards the same place, right? Okay. I won't write it down. I think y'all are okay with that. Okay, so this is in here. I kind of went a little too fast there. This is the general idea of the limit of a function at some value x equals a. So when I say x equals a, what I mean is, in all these problems we've been doing, like x approaches 2, x approaches 0, right? This number right here is a. So when we're talking about the general idea of a function, the limit of a function a, basically, when we're trying to find the limit, we are inspecting the behavior of the function near a, right? Near the value. We do not care about the actual value of the function at the a. We inspect the behavior of the function. We can approach from the left or the right side. When we approach from one of the sides, one of the following can occur. So when we're coming in from one side, is that a question or twirling? Okay. When we actually approach from one of the sides, the function can actually just like approach a value. That would be like, let's say it's doing that, right? Like coming in, it's actually approaching a value. That would be this. The function could oscillate infinitely many times. That was that sine one that we saw. Okay? Or the function approaches either positive or negative infinity. So it could take off like that, like an asymptote, or go the other way. Those are pretty much the 3 different scenarios that we can see when we're coming in from one side. Understand? Okay. Remember, we do not care what is happening at the value x equals a. This is what makes this calculus, right? That's the whole point, is we don't care what's happening there. It's what's around it. Okay, I think I accidentally repeated that. Oh, no. This is just left-hand limit, right-hand limit. You understand that? I don't need to read that, the difference between the two. And then the notation. Here was a notation. Lim. Now, for some reason, when I typed this into this system, it didn't put this below the limit. Normally, it's put below, but you can put it to the side also, just as long as it's subscripted and not written all along in one line. So limit x approaches a, negative sign means from the left, of the function equals L. L is the answer, okay? It's the thing that we're approaching. So that answer could be 1, it could be 0, could be 8, could be 4, could be negative 0.25, could be infinity, and it also could not exist, right? Does not exist is a possibility. When we want to approach from the right, we use a plus sign. What if we want to do a limit and we want to approach a value from both sides? How would we say that? If I want you to actually inspect both, then what I do is I write limit x approaches a, and I do not put a plus or a minus. What that's telling you is that you must do both. Okay? And you will only have an answer if you get the left-hand limit and right-hand limit to exist, and they are the same. In that case, we will say the limit exists. Yes?
If one of them doesn't exist and one of them does exist, do you have to put it that it doesn't exist?
That's right. If one of them does exist and the other one does not, you would say it does not exist. I'm going to do some examples, all right? Lim, so this is again, this arrow means you're letting x approach a. Lim means you're doing a limit. Yeah, okay, so let's go back to this right here. What is the left-hand limit of this function? Right-hand limit? 4. What is the, I didn't say as x approaches 2, I should have said that. What's the left-hand limit as you approach 2? It would be 8. Left-hand limit as you approach 2 would be 4. What is the limit? What is the limit, if I wrote this down, if I just wrote that down right there and asked you what's the answer, what would you tell me? Does not exist. Why? Because they're not the same answer. From the left it was what? 8. From the right it was 4. The left and right hand limits do exist, but they're not the same. And in order for me to say that this is an answer, they have to be the same. So this would be does not exist. Is there a question, Diego?
What happens if, like, say there's an open point at like x equals 1? Would that approach 2 as it approaches from the left?
If there was at 1,
Yeah.
you want me to put a hole here?
Yes.
And then what? Still talk about approaching 2?
Yeah.
It's okay because 1 is too far away from 2. Far, near, we start to get subjective. But the thing is, I can get close to 2 without that hole interfering with me. Now, what if you put a hole at 1.999? It's okay because I can still go to the right of it. I can still find a point to the right, and I could just magnify myself in there. All right. The whole idea of near and far in calculus is very, we're kind of waving the white flag at the near and far idea. And are there any math majors in here? I know I have at least one. Okay, so a math major actually has to come up with a more precise definition. Near and far doesn't fly in mathematics, like in pure mathematics. So we use what's called delta epsilon proofs, and that's how we do it. But you'll see that later. In a class like this, there are calculus classes. If anyone here has ever probably taken a class, if this is your second time taking Cal 1, you may have actually been exposed to delta epsilon proofs for limits. My philosophy on that is you are not ready for delta epsilon proofs because it's logic. You have to have an entire course of logic and how to do proofs before you can even understand how to work with that stuff. So I'm not a big fan of it, and you can survive through the entire calculus sequence without ever having to do a delta epsilon proof. So you'll be fine. All right, so we good with this? Left-hand limit, we would have an answer. Right-hand limit, we'd have an answer. The limit itself, the limit, this is kind of like the big guy. The limit doesn't exist here. How about this one? Does the left-hand limit exist?
Yes.
Right-hand limit?
Yep.
What's the limit? How about just the limit? Does not exist. Because there's a break in the graph, right? There's a jump there. Left-hand limit exists as we're approaching 2. Left-hand limit, yes. Right-hand limit? Are they the same? Yes. So the limit, if I just wrote limit, x approaches 2 of this function would be 8, see? And that tells you, like if you let's say you had no picture here, and somebody was, hey, I've got this function. It's a really cool function. You should meet it one day. And the limit as x approaches 2 of this function is 8. You would already know this, right? You would already know this. Here's what you could do if someone told you about their friend that was that function. You would already be able to do this. You would know that much about that graph, wouldn't you? Now I put a hole here. Why did I put a hole here? Because I actually don't know what's happening at 2, right? It could turn out that this function is filled in here. It could be a point up here, or it could not even be there. But this information tells me that the graph looks like this, right? So that's a lot of information given to me right there. Okay, well, let's look at the next one. Limit doesn't exist, right? Limit doesn't exist. Left-hand limit? Yes? Right-hand limit? Yes. Keep in mind, the left-hand limit, that point does not matter, right? Right-hand limit, the fact that it's a hole has no impact on my answer, right? Okay. right here, this point at 1. Left-hand limit? Is there a left-hand limit here? Yes? Right-hand limit? Yes? Are they the same? They're headed towards the same point. This is the example from earlier. What was that y value that it was headed towards? Negative 0.25. So I could say here, limit as x approached 2 of this function is negative 0.25. So again, without putting the plus or minus, it's implied that it's both from the left and the right. Oh, I'm out of time. Man. Okay, well, we didn't get an opportunity to do this last example. So do your best on your homework, which I did not even put the assignment up here. Okay, I'm going to have to email you the assignment. Okay, so check your Canvas email. I'm going to go to my office right now. I'm going to upload our lecture video, and I'm going to get your assignment and send it to you to do out of the book. All right? Everybody have a great day. A great weekend. We'll see you on Monday. Do your homework from 1.3.